All right, so from my understanding, last class you learned about stereochemistry, like what is a stereocenter and how to distinguish between, how to distinguish between meso, diastereomers and enantiomers, stuff like that. So we're not going to have a review on that because of our limited time. But you can definitely work on that during office hours or during your study group time. So today I'm going to try to keep the lecture brief and leave some time for people to ask long questions in the end. And I will stay for a little longer after the lecture to answer any questions you might have. Okay, so today we're going to keep talking about stereochemistry, and here's an overview. Ooh, something happened. Right, here's an overview about what we're going to cover today. We're going to talk about stereochemistry of alkene. We're going to talk about cis versus trans and E versus Z. It doesn't matter if you don't know what they mean. I'm going to go over them very quickly, and I'm sure you will be able to catch up very soon. And then we're going to talk about absolute configuration of alkanes, R versus S. And it doesn't matter, again, if you don't know what that means. And I'm sure by the end of the lecture, you will have a very good understanding of how to assign absolute configurations. So let's jump in. Okay, instead of me telling you what cis and trans are, I'm going to test your chemical intuition. So here's a picture of an alkene. Tell me if it's cis or trans, just shout it out. It's okay if you get it wrong because you don't even know what they are. Just tell me what it is. And I'm gonna sit here and wait until somebody says something.
Is this cis?
It's cis. It's cis, right? Why is it cis?
I guess because
because it looks like this, right? That's what you would, everybody's pointing up. Okay, so good. See, you know what cis means now. It literally means the things are pointing to the same direction. What about this? Cis or trans?
Trans.
This would be trans, right? Because the two groups, two H's, are pointing at opposite directions. What about this?
Trans.
This is also trans, right? Because their two longer alkyl chains are pointing opposite directions. So there you go. I don't even have to teach you what cis versus trans means. You already know. And cis versus trans works for simple alkenes. And some of you might want to ask, what does simple alkene mean? Well, if you can look at a molecule and then determine immediately if it's cis or trans, it is a simple alkene. But our system doesn't hold all the time. See, the first part of our lecture is done. Cis versus trans, you already know it. What about this one, cis versus trans? The first molecule, let's say. Anyone tell me? Can you tell, like just by looking at it? It's a trick question, so, you know. It's okay if you don't know what the right answer is, but I want you to share your thoughts with me. Why is it so difficult?
You have to assign priority.
You have to assign priority, right? You can't just look at it and say, okay, this is cis or trans, because it has 4 different things attached to it, and you can't tell right away. There aren't any big groups attached to the carbons that we focus on. So how do we assign the configuration for this type of alkenes? Well, we're going to evoke something that's called E versus Z. So here's the rule: higher atomic weight, higher priority. So if you have a higher priority, it means that you're going to be numbered as number 1. If you have a lower priority, you will be numbered as number 2. And if you see the 2 higher priority groups on the opposite sides, they're E. If the higher priority groups are on the same side, the configuration is Z. So Z for they are on the same side. It's terrible, it's corny, but it helped me remember, you know, when E versus Z. So now I'm going to stop sharing my screen and move on to the board. Everybody see the board? So I'm going to do a lot of drawings, and please draw in your notebook or your paper, whatever you have. So remember the two molecules we just saw, two complicated ones? I'm going to draw them on the board. Let me pull my computer closer. This is CH3. So how do we, assign priority in this case? Well, we're going to first cover half of the molecule. That's very important. Which half do we cover? Anybody knows? Take a guess.
The right.
We're going to cover the right half, right? So it doesn't matter. You can cover the left first. Just don't cover the top or bottom. That's the wrong way to cover it. So let's cover the right part first. I'm going to just draw the left part out. Here I have my bromine on top and my fluorine on the bottom. So what do I do next? Somebody other than Nestor talk to me.
You determine which one's the higher priority molecule.
Yeah, we determine which one's the higher priority. So we determine the priority based on what?
Weight.
Atomic number.
Atomic number, yes. So which one has the higher atomic number, bromine or fluorine?
Bromine.
Bromine has a higher atomic number, right? If you remember the column of halogens in your periodic table, bromine is on the bottom of fluorine and chlorine. So I'm going to assign the bromine number 1 and the fluorine number 2. Now I'm done with the right half. Then what do I do?
Do the other side.
Do the other side. Sounds good. So I'm going to draw out the right-hand side of the molecule. I have a Cl on top, CH3 on the bottom. So this situation is a little bit different. I have an atom on top and a methyl group on the bottom. What do I do in this case? Anybody can guess?
Priority goes to the methyl group.
Sorry?
Priority goes to the methyl group.
Why is that?
Well, I guess if you compare atomic weights, I'm assuming CH3 probably has a higher atomic weight, but also CH3 is a more complex molecule.
Right, so that is the part we have to be careful with. I really appreciate the fact that you're sharing your thoughts, and you're definitely on the right track. However, here in this case, we have to look at the atom directly attached to the carbon that we're focusing on. That's this carbon. So the atom that's directly attached to the carbon on top is chlorine. What about the bottom?
A carbon.
It is a carbon, right? So who has higher priority?
The chloride.
The chlorine would have higher priority, even though the CH3 seems like a bigger group. So that's the part we have to pay extra attention to. So chlorine gets 1 and methyl gets 2. So now we can look at the molecule as a whole, right? So we have higher priority bromine on top. It goes this way. We have higher priority chlorine on top as well. So is it E or Z?
Z.
It's going to be Z. Why?
Because the higher priority, I guess, atoms are on the same side.
You're absolutely right. They're on the same side, therefore it is going to be a Z. Any questions so far regarding how we assigned the configuration to this alkene specifically?
Oh,
Nope. Yes.
I have a question. Yeah, so if it was E, would the arrows be flipped, like in opposite directions?
Yes, you're absolutely right. If it was E, then we would have an arrow going up and another arrow going down.
Oh, okay. And also, so we split the molecule to do like the priority stuff. I'm
Yeah.
just like, oh, okay, thank you.
Yes. You don't have to draw it this way. This is just to show exactly what to do in the beginning when you're first introduced to this. In the future, you can just look at it and then start numbering in on the molecule that's intact. It really depends on what you're comfortable with. So don't worry if you think this looks weird. You don't have to do it this way.
Okay, thank you.
All right, you're welcome. So let's practice a little bit more. I'm gonna move on to another molecule that is slightly different. So I'm going to introduce you to its geometric isomer. Geometric isomer means that they have the same molecular formula, but they're organized differently geometrically. That means you have different atoms connected to different parts. And I'll illustrate that on the board in just a second. So we still have this overall structure, but our atoms are mixed up this time. So I have fluorine on top, bromine on bottom, and the right-hand side of the molecule does not change. I just flipped fluorine and bromine. So let's assign the absolute configuration for this alkene. What did we do in the beginning?
You cover one side.
You cover one side, right? I'm going to cover the right-hand side. No, we just focus on the left. We have fluorine and bromine. So, who has higher priority?
The bromine.
The bromine has higher priority. Good. So fluorine gets number 2. What about the right-hand side? We just did it.
Chlorine.
Yes, thank you. Chlorine has higher priority and methyl gets number 2. So this time, my left arrow is going to point down, whereas my right arrow is going to point up. So what configuration is this?
E.
It's going to be E, right? Because they're pointing opposite directions. Okay, so great. You now know the fundamentals for assigning E and Z, but we're going to move on to some more complicated examples. Anybody has any questions so far regarding this that we just did?
I have a question.
Yes.
So does E and Z directly correlate to like cis and trans? So it's like if it, yeah.
That is a wonderful question, and I absolutely love that you just asked it. I'm going to go into that in more details later in the lecture, so can you hold that question for me?
Yeah, thank you.
Thank you. Okay, so that was a very important question, and I'm pretty sure that when you take the actual course, it's going to come up during the lecture, so pay extra attention to this. All right. So more complicated molecule. Here's the puppy that I'm going to draw. I got a bromine on top, an ethyl on bottom, an OH on top, and this on the bottom. Okay, so I'm going to focus on the first double bond. That is the double bond on the left. Even though there are 2 double bonds, I don't care about the second one. I just care about the first one. Okay, so what do we do first? Let me adjust the board a little bit so that it doesn't.
Cover one side.
We're going to cover one side. We're going to ignore the right-hand side first. So who gets higher priority in this case? We have an ethyl and a bromine.
The bromine.
The bromine gets higher priority because?
It has a higher atomic number.
Bromine has a higher atomic number as compared to what?
The carbon in the ethyl group.
Yeah, it has a higher priority compared to this specific carbon of the ethyl group. We're not looking at the entire ethyl group. We just focus on the first atom that is different, that is directly attached to this carbon. Okay, so bromine gets number 1 and the ethyl gets number 2. Now let's move on to the right-hand side of the molecule. What do we do in this case? I have a carbon right here and another carbon right here. So they're both carbons. Do they have the same priority?
You have to look at the groups
right?
attached to the carbon. You have to look at the groups attached to the carbon.
One by one. Very important. So we have 2 groups that are obviously very different, but the atoms that are directly attached to the carbon are the same. So in this case, we're going to do this technique called DOT technique. It's really silly, the name. I found it on Master Organic Chemistry's website. You can call it whatever you want. But basically, we're going to move on to the next atom. So here's how I'm going to do it. I'm going to identify the first carbon that's attached to the carbon we're focused on. So here's the first carbon. Here's the first carbon on top. They're the same thing. So I'm going to write out the things that are directly attached to those carbons. So let's start from the bottom. What hybridization is this carbon? Is it sp3, sp2, or sp?
sp2.
It is sp2, right? Because it's a trigonal planar geometry. Okay, so what's attached to this carbon? Let me draw out a little hydrogen right here.
So another carbon and another hydrogen.
Yes, you're absolutely right, Emma. Thank you. So we're going to write everything that's attached to this carbon in a way such that the higher priority atoms are written first. So we have a carbon and a hydrogen. So I'm going to write carbon, hydrogen. And because this is an sp2 hybridized carbon, I'm not going to write a third thing. Okay, so what about this carbon on top? What do I write in the parentheses here?
Oxygen and hydrogen.
We have one oxygen and how many hydrogens? How many hydrogens are missing on this carbon that I'm doing? We have two hydrogens, right? So I'm going to write oxygen, hydrogen, and hydrogen. So let's compare these two sets of atoms. The first one for the top is oxygen, whereas the first one for the bottom is carbon. Now we have something different. Who gets higher priority?
The top one.
The top one, why?
Well, I like, since like if you're just comparing O and C, you're just like looking at which one has the higher atomic number. So
yeah, you're absolutely right. Whichever one's heavier, that gets priority. So our oxygen is going to be number 1, our carbon is going to be number 2. Now we're done assigning priorities. So in this case, on the right hand side, my arrows are pointing up. My arrow's pointing up or down.
Up.
It's point up. What about on the right hand side?
Up.
It's going to also point up. So what configuration is this? Diene. I mean, if we focus on this part only.
Z.
Z.
It's going to be Z, right? Because they're on the same side. Any questions regarding what we did for this molecule?
I have a question.
Yes.
How do we know to order it that way, like the parentheses?
I'm sorry.
How do we know to put the C before the H, like in the parentheses?
How do I know that?
Yeah, like how do we know what order to?
That's a good question. So the technique requests that you put higher priority atoms before lower priority atoms in the parentheses. That's the only way it's going to work.
Okay, thank you.
Yeah, so just remember that every time you move on to the next atom. Okay, more questions regarding what I just did?
Why didn't you include another C for the bottom one?
Right, because this carbon is sp3 hybridized, sp2 hybridized. Therefore, there are 3 things attached to it, right? So we're ignoring this carbon right here. We don't have that carbon.
That makes sense. Thank you.
You're welcome.
Where did you get the other H for the OH part?
Right, so see right here, I'm going to zoom in on this top part so that you see it clearly. You see it? Yes. Okay, so this is the top bar, and that's my OH right here. This means one carbon, correct? So what hybridization is this carbon?
SP3.
It's sp3, which means how many things do we have attached to it?
4.
4 things. So what are we missing here?
2 H's.
We're missing 2 H's. So there you go.
Okay. All right.
Cool. No, don't worry about it. All right. So are we good? Can we move on to more confusing and difficult things? Cool. Let's move on. All right, so I'm pretty sure some of you now have a sense of the difference between cis, trans, and E and Z. Cis and trans provide relative configurations, and it's very easy to determine if a molecule is cis and trans, whereas the E and Z version provides the absolute configuration, and it's kind of difficult. You have to look at it and think for a while in order to assign the configuration. So is it okay for cis, trans, E, and Z to disagree? In other words, does E correlate directly with trans and Z with cis? So that was, I believe, question that, who asked me that question earlier? Arifa? Was that you?
Yeah, that was me.
Right, it was you who asked me that very important question. So the answer is that they do not always correlate. That's very confusing, right? Because in the previous example that we saw, let me just draw you this. Cis or trans?
Trans.
Trans. E or Z?
Z.
It's going to be Z or E?
Oh, I think it's E.
You think it's E, why?
Wait. Because actually that doesn't make sense because they're the same thing. If you like go on, I guess, to the every other carbon is like the same.
Right, so let's go over that. You're absolutely right, Anthony. Just in case some other people are not following up, I'm going to explain this in more details. So let's split the molecule from the middle, right? Here we have an ethyl versus a methyl. So which one gets higher priority? They all have carbons directly attached, but this one, based on the dot technique, what do I write in the parentheses for this carbon?
Would you put C1, then H, and then C2, and then another H?
How many am I putting there?
Oh damn.
It's okay, it's okay. Not trying to put you on the spot just because you're the only one who's talking to me right now. Okay, so let's take a look at this together. We have one carbon, right? What's this carbon attached to?
2 hydrogens.
It's attached to 2 hydrogens, you're absolutely right. What else?
A carbon.
A carbon. What about this?
Three hydrogens.
3 hydrogens, thank you. Who gets higher priority?
The top.
The top, right? Because we have carbon versus hydrogen. So for simple alkyl chains, the longer chain gets higher priority. That's always the case. If only you're comparing 2 alkyl chains, the longer chain gets higher priority. Because at one point you're going to encounter this problem. And one of them is going to have 3 hydrogens on it, whereas the other has a carbon and 2 hydrogens. So if you're, let's practice this. If we go to the right-hand side, which one gets higher priority?
Bottom one.
Sorry, Karina?
The propyl group.
Yeah, the bottom gets higher priority. Ah, that was 1. Because it's a longer chain, and at this point, we're going to have carbon H, H, whereas for the top, we have H, H, and H. Anybody has questions regarding this? Okay. Let's move on to something more confusing. This is, so we have trans, and our arrows are pointing opposite directions. So it's E or Z.
E.
It's going to be E. So in this case, our trans, cis, and EZ correlate very nicely with each other. But I can give you an opposite example where they do not agree. So let's look at another example of this. Have an H on top, CH3 on the bottom, very long alkyl chain here, and a CH3. Again, cis or trans?
Trans.
Cis or trans?
It looks trans.
It looks, okay, I know what's confusing. So here we have 2 methyls. They're the same thing. If we're just focused on the 2 methyls, do you think it's cis or trans?
Cis.
It's going to be cis, right? So if you encounter a very simple alkane that looks simple and it has 2 groups that are distinctively the same and they point the same direction, that's going to be a cis. So that's the confusing part about assigning cis versus trans, because what are you looking at, right? So if we focus on the methyl groups, it is going to be a cis. But what about E versus Z? Let's assign priorities. Let me focus on the left-hand side first. Which alkyl chain gets higher priority?
The top.
The top, right? Because it's a longer chain. It's very simple, and the bottom one is a methyl, so it's always number 2. What about the right-hand side? I have an H versus a methyl. This one should be very easy to you guys.
The bottom gets higher priority.
The bottom that has higher priority. That's absolutely right, because the first atom is carbon versus here it's a hydrogen. So my arrows are pointing up and down. Therefore, it is E or Z.
E.
It is going to be E. So in this case, it is cis and E. Cis versus trans and E versus Z do not correlate in this case. So be very careful. It's okay to use either during an exam. Just don't ever mix those up. So if I use the cis naming for this molecule, it's going to be called what? Cis. I'm going to number the longest chain. So that is cis. 1, 2, 3, 4, 5, 6, 7. So I have longest alkyl chain that is 7 carbons. So I have cis, and you just name this molecule the normal way that you would. So what do I start with?
One comma 2 dimethyl.
So I start here. So therefore, this methyl is the beginning of my longest chain, which means it's not a substituent. So are we dimethyl or just methyl?
Just methyl, I'm sorry.
Yeah, no, don't worry about it. It's confusing because I wrote it this way, just to confuse you. So, okay, it's methyl. So methyl is on which carbon? carbon 1, 2, 3, 4, 5?
3.
Carbon 3, right? So it's cis 3-methyl. Where's this alkene? Is it between carbon 2, 3, 3, 4, 4, 5?
Two and 3.
Yes, it's between carbon 2 and carbon 3. Therefore, we're just going to call it 2 because it starts with carbon number 2. And how long is the chain? We have 7 carbons in the chain. So what's the prefix for 7? I honestly don't remember. What is it?
Heptene.
Heptene. Thank you. Heptene. So that is the name for this alkene if we use cis versus trans naming. However, if we use E and Z, we're just going to change the first thing. That is E, and you write the same thing on the bottom.
I have a quick question.
Yes, yes. What about it?
So H comes before M in the alphabet, right? So when do you H comes before M in the alphabet, so when do you have to alphabetize it and when do you not? When you're naming.
So when it's a substituent, you alphabetize it. By substituent, I mean things coming off of the main chain. Whereas this heptene is the chain itself, so you don't alphabetize it.
Okay, thank you.
You're welcome. Okay, so good. Given the time constraint that we have about half an hour left. I'm going to move on to the next thing. So let me share my screen with all of you again. So now we're done with the very first part of the lecture, which is stereochemistry of alkene. You've learned cis versus trans, E versus Z, and you know exactly how to assign them. So I'm not worried about that at all. The more difficult part is stereochemistry of alkane, R versus S. So here are two pictures of my cat. They're identical. They're mirror images of each other. So my cat's name is Remus. But how do I distinguish between those two pictures, right? One of them, we have him facing the right. In the other picture, we have him facing the left. So if I want to distinguish those two mirror images of each other, I need to come up with some sort of scheme. And some old white dudes in the past, as the field is dominated by old white dudes, even as of now, came up with R versus S naming system. So we're going to learn how to assign absolute configuration for chiral molecules. And this is just for the alkane. So that's the end of my PowerPoint presentation. We're going to move on to assigning absolute configurations for alkanes. My board is about to fall down. Just give me a second. Okay. So let me show you a molecule that looks like this. I have the wedge with the fluorine, dash with the hydrogen, with a methyl in the plane and a bromine in the plane. Everybody see it? Okay, so the first thing we're going to do is to identify the chiral center. Which one of them is the chiral center? Should be a very obvious question.
The carbon.
The carbon's the chiral center, right? So I'm going to put a little star on it just to remind myself that's the chiral center we're focusing on. So when we're ranking, we don't rank the carbon. Okay, so step number 2 is to rank those 4 things on the carbon center based on the rules that we just practiced, which is higher atomic weight, higher priority. So how do we rank those? Who gets the highest priority?
Bromine.
The bromine is number 1. Who's number 2?
The fluorine.
Fluorine is number 2. Awesome. What's number 3?
Carbon.
carbon.
Close number 3. That's awesome. So, which leaves us number 4 to be hydrogen, which is the lightest thing you could possibly have on there. All right, there we go. We're done with ranking. So the third step is the most difficult step, and that's the step where people make the most numbers of mistakes. So let's look at the molecule, and we want to rotate the molecule in our heads such that the lowest ranking group is going into the board. Do I have to rotate this molecule in my head, or is it already that way?
It's already that way.
It's already that way because my lowest ranking group is this hydrogen on top, and it's bonded to a carbon with a dashed bond, which means that it goes inside the board. So next up, to help you guys visualize better, I'm going to draw the Newman projection for the first carbon. So we all remember how to draw Newman projections. We look down a bond and we draw the things attached to the carbons. So here we're only looking at this carbon. So we're only drawing half a Newman projection. So I have my center carbon right here. I have fluorine on top, CH3 here, and Br here. And I write down their numbers. They're 1, 2, and 3. Any questions regarding how I did that? No, we're all clear how I converted this picture to the Newman projection? Okay, wonderful. So our Newman projection is numbered. We have 1, 2, 3 going clockwise or counterclockwise?
Counterclockwise.
It's going counterclockwise. Therefore, we're going to call this configuration S. That's just arbitrarily assigned. We just call it S. I guess if it was up to me, I would call it some cooler letter, you know, like X, but yeah, I think it came from some German word. But if it goes counterclockwise, we call it S. But how about if it goes clockwise? Can anybody guess?
R.
Sorry?
R.
It's going to be called R. You're absolutely right. So this is the difference between S versus R. If you draw the Newman projection, it goes counterclockwise, it's S. If it goes clockwise, it's R. So, awesome. Here I'm going to add a little bit difficulty to this.
I have a question.
Yes.
When do you know if it's like, how do you know if it's going clockwise or counterclockwise in the Newman projection?
That's an important question. Okay, so, and I have 1, 2, 3. I am tracing the number from the smallest to the biggest. 1 is here, my 2 is here, my 3 is here. Which direction am I going?
Counterclockwise.
Counterclockwise. So is that clear?
Yeah, thank you.
You're welcome. Okay, so now I'm going to add a little bit of difficulty and see if you guys can nail this one. That's case number 2. So I have the same carbon. This time my fluorine's going into the back and my hydrogen is going to the front. And I have CH3 and Br. I'm going to just number those atoms the way we did just now. Step number 1 and 2, I did those for you. Step number 3, who remembers what it was?
Rotate the molecule until, I don't know if it was the hydrogen was facing inside the board.
Yes, you're absolutely right. We're going to rotate the molecule in our head so that the hydrogen or the lowest ranking atom goes into the board. This is kind of difficult because now our hydrogen is directly pointing at us. It would mean that we would have to rotate it 180 degrees, and I understand that it's difficult for people who just started learning organic chemistry. So here's a trick. We're going to just ignore the hydrogen as we did for the other molecule right here, and we're going to just finish this problem the way we did for the other one, and then we're going to flip our answer. So I'm going to draw the Newman projection for this. I ignore the hydrogen on top. I have fluorine, methyl, and I have Br. And I have 1, 2, and 3. Am I going clockwise or counterclockwise?
Counterclockwise.
I'm going counterclockwise. Therefore, I'm supposed to be an S. But because we did not flip the molecule, and we should have by 180 degrees, we're going to flip the configuration, and we're going to assign this to be an R. And we can only do this when the lowest ranking group is pointing directly at us. We cannot use this technique when the lowest ranking molecule is pointing toward the back or in the plane of the board. Any questions so far? It's just a little trick to prevent you from having to rotate a molecule in your head. But if you want to rotate it, no problem. You can absolutely do that.
Can you repeat the last part you said about like?
About?
Oh, about like the trick, like the without rotating it, I guess.
Yeah, absolutely. So let's observe this molecule, right? What's the difference between those two babies?
Oh, so I guess everything is the same, but it's just that the hydrogen is now like it's not a dashed line anymore, it's a wedge, so it's going out towards us.
Absolutely, you're right. So the difference is that this bond is coming out towards us, whereas this bond is going into the plane of the board. So that is a very important distinction, because the step 3 of the method for assigning absolute configuration says we have to rotate the molecule until we have the lowest ranking group going into the board. So for the first case, it's already into the board, so we don't have to do anything. We just assign the absolute configuration. But for the second one, it's not the case anymore. We have to rotate it in our head. By how many degrees can you imagine?
180.
By 180, why?
Because like wait.
No, it's okay. Your answer is correct. I know it's kind of hard to explain, so I'm going to explain it to everybody for you. Is that okay?
Yeah.
Okay, so let's pay attention to these two bonds, right? So we know that this carbon is a tetrahedron, which means that we have 2 of the bonds in the plane of the board and another 2 bonds going in and out. One goes directly pointing at us, the other one points directly into the board. So they're 180 degrees apart. In order to move the front one to the back, it would have to be rotated 180 degrees. Make sense?
Yeah.
Okay, so good. Now we know if we were to actually follow step 3 and rotate it in our head, it would have to be rotated 180 degrees. But we don't want to do that. I don't want to do that in my head. I suck at 3D visualization. So I'm just going to introduce this little trick that you do the problem as if the hydrogen is in the back. You assign the absolute configuration based on the method that we just learned, and then you flip the absolute configuration in the end. Okay. It only works when your lowest ranking group is pointing directly at you. If you have your lowest ranking group in the plane of the board, you cannot do that. You must rotate it in your head. And for the third case, I don't think we have enough time to cover because I want to leave some time for people to ask questions that they probably want to ask. So I left a link in my slides. It's the last slide. So if you go into that website explains very in detail how to take care of each scenario. And if you have any questions regarding how to practice rotating molecules in your head, come to my office hours tomorrow or speak to any of our wonderful teachers in the group, send me a message, whatever. And I apologize for not being able to respond to emails on time because I have a full-time research graduate student job and I work 16-hour shifts in a day, and that sucks, 7 to 11. So I don't have much time to look at my computer when I'm in the lab working. So this is the end of my lecturing part. So now I open the floor to all of you for any questions you had during the class that I didn't answer.
Oh, so I still had questions about the E or Z.
Yeah, sure. Julia.
Yeah, so for the Homer, for example, they're like the longer chains, for example, what if they're the same exact chain on one side?
That's a very good question. What if they're the exact same? Can you assign priorities? It's not a true question.
Oh yeah, that's like my question, because I feel like you can't assign priorities if it's
Cannot assign priorities. Yes, you're absolutely right. So in that case, can you assign E or Z?
No.
No, you cannot.
Oh, okay.
Yeah, so if you see the same thing on one side, then there's no E or Z.
Okay, thank you.
You're welcome. Other questions?
I have a question also about the cis and trans stuff.
Yes, of course.
For the very last example that we did, you said that we can identify it as a cis molecule because the two methyl groups were pointing down.
Yes.
But I was wondering if one of the groups was anything but a methyl, would it still be cis or would it be trans?
So I just had this, right? Cis, and I don't remember what I had on top, but it doesn't matter. We have two of the groups that are same, and if we had another methyl on top, we ran into the situation where Julia just brought up. You know, we have the same thing. Therefore, there's no cis or trans. So imagine I put something else on here. Is it cis or trans? I don't know. I can't tell because you have three of the groups that are the same. Only this group that's different, but how do I rank it? How do I rank those? We have priority number 1 and 2, 2, 2.
Okay.
So if you see, in this situation, if you see three of the groups that are the same, there's no cis trans or E and Z.
Okay.
Yeah, so there will be cases where you cannot rank them and just don't assign. And there probably will be trick questions like this during our exams. If not for this program, there definitely will be questions like that for your actual course. So pay attention to that.
Thank you.
You're welcome. Any more questions? We have about 10 minutes.
Yeah, I know you went over the stuff like cis and trans, but can you like re-explain the E and Z thing again?
Yeah.
Yeah, like
so,
yeah.
Let me find an example. Okay, I have this good example that I drew up, but I didn't get a chance to use. Let me use that. Cis or trans?
Is it cis?
We're going to call it cis because we have the same two groups on top and they're going this way. They're going this way. So we're going to call it cis. Now we're going to try to assign the E versus Z absolute configuration. So let me split the molecule in half. What do I do now?
You pick one side.
Pick one side. Which side do you want to work on?
The left.
The left
side.
side. Okay, sounds good. So the left side, what is the first thing that's attached to this carbon?
Carbon.
We have a carbon. What about this on top?
Carbon.
We have a carbon, so that doesn't help at all. Right. So we're gonna use the dot technique, move on to the next thing. So I'm going to dot my carbons just to remind myself that these are the carbons I'm focusing on. I don't care about the rest yet. So for the top one, what do we have attached to this carbon?
Like for the one you have a dot on?
Yes.
2 C's and an H.
I have CCH. Good. What about the bottom?
OHH.
We have OHH. Who gets higher priority?
The oxygen.
The bottom gets higher priority. So I got 1 on the bottom, 2 on top. Okay, so let's move on to the right-hand side.
They both have C's.
They both have C's. You're absolutely right. So we're going to
dot thing.
Yes. So for the top, what do I have here? It's the same as this.
Yeah. CCH.
We got CCH. What about the bottom?
CHH.
We got CHH. Okay, so the first thing is C. Still doesn't help. What about the next thing? We have C versus H. Who gets higher priority?
The top one.
The top one, right? So we have 1 on top and 2 on the bottom. So now we can feel comfortable enough to assign E versus Z. So here my arrow goes down. Here my arrow goes up. Is it E or Z?
Like what makes the arrow like it's E, right? Z
It's
E?
E, right? So because my arrow head points towards the higher priority. So my higher priority here is on the bottom, therefore my arrow points down. But on my right-hand side, my higher priority is on top, therefore my arrow points up. So they're going opposite directions.
Mm-hmm.
So this is an E.
Okay. That makes sense.
All right, cool.
Thank
Any
you.
more questions, people?
Going back to RNS configurations, what happens if the highest priority molecule is going out of the board? So like it's a dashed line.
Highest priority group is a dashed. Let's practice doing that. We have 7 minutes left, so why not? We can deal with this. So let me just draw a stereocenter carbon. So you're asking what would happen if we had the highest priority going out?
Yeah.
Or going in?
And going out. So like for the example you gave like a few minutes ago with hydrogen going out, or no, going into the board.
Going into the board, you mean? So that's dashed.
I'm trying to remember. So for example, homework question, bromine is going out of the board, even though it's the heaviest molecule.
Okay. What else do we have on here?
So hydrogen, chlorine, and a carbon.
Okay, so which one's which? Who goes into the board?
So into the board is bromine, and then out of the board is chlorine.
Bromines?
So yeah, instead of the wedge would have chlorine instead.
Okay. Chlorine, bromine, and what else? What's on the left?
On the left, it's hydrogen.
Hydrogen. What about the right?
And a methyl.
And a methyl, CH3. Okay, so let's start ranking. Oh, this is the most difficult situation that you will ever encounter, in which the lowest priority is in the plane of the board. So we cannot use the normal method. We cannot use the flip method. Gotta do it in your head or draw it out. Okay. So let's rank them first. Bromine is the heaviest, chlorine next, methyl third, hydrogen fourth. Anybody has any questions regarding how I numbered them? No? Okay, good. So we can move on to step 3, where we want to rotate the molecule in such a way that hydrogen goes into the board. How do we even do that? Well, we have to visualize the octahedron in our head, right? It's basically 2 planes going this way. One in the plane of the board, the other goes in and out. So if we rotate the molecule, let me just draw these bonds out. My ultimate goal is to put the hydrogen here or here, right? So either way works. And I want to, if I put the hydrogen here or here, everybody else would have to move as well. So let me just put the hydrogen here, going inside of the board. Which direction are we looking at the hydrogen now? Am I looking from here? Am I looking from top or left or bottom?
Can you repeat that?
Yeah, absolutely. Sorry, my question was fast and unclear. So we're going to pretend this is a 3D thing, and we're walking around it. And we want to walk to a point where the hydrogen goes into the back, so we can't see it anymore. So this is like doing a Newman projection. We want to imagine from which angle we look at the carbon so that we cannot see the hydrogen because it's going directly into the board. So if I put my hydrogen here into the board, from which angle am I looking at this carbon H bond? Am I looking from right or left or bottom or top?
I thought you'd be looking from chlorine, along the chlorine to carbon.
Along the chlorine carbon bond?
Yeah, if H was behind it.
So we gotta remember that the chlorine comes directly out of the board.
Okay.
And this H is in plane of the board. Therefore, they're not 180 degrees apart.
Okay.
Yeah, does that clear things up? They cannot be 180 degrees apart.
Yes. Maybe. I'm still just, because I thought your question was how would we look at the molecule if we wanted to see the hydrogen behind it?
If we don't want to see the hydrogen behind it.
Oh, if you don't want to see it. Oh.
If we don't want to see it.
Okay.
Yeah, sorry, I was speaking so fast. It was not your fault. Okay, so if we don't want to see the hydrogen behind it, I propose that we look from here. So the hydrogen, we can't see the hydrogen. We look directly at the CH bond so that we can.
Oh, okay, yeah.
Right, makes sense?
Mm-hmm.
All right, so.
I have a question.
Yes.
So for example, like I have the model kit, but I'm trying to imagine this in my head. So if we have like 2 pens, if the H and CH3 are in the same plane right now,
If the H and what in the same plane right now?
So if the H and CH3 are in the same plane right now.
They're in the same plane right now. Mm-hmm.
And you said there are 2 planes that are like crossing each other, right? So is it always going to be the case that if you put H in the back, then the CH3 has to go in the front?
You're
like they have to stay on the same plane, right?
Mm-hmm.
They always have to stay on the same.
You're absolutely right. If my H is going in or out of the board, my CH3 has to go in and out of the board.
Okay.
In or out of the board as well.
Got you. Thank you.
Yeah, you're welcome. So actually, here I gotta move these bonds a little bit because I'm directly looking at this and my H is invisible. So let's just draw this as if I'm just looking at, my H is totally invisible. Here, it's in the back. What's in the front if I look at my carbon this way?
CH3.
Your CH3 is in the front, right? Because your H and CH3 are in the same plane. So if you move them like this, your H goes in, your CH3 must be pointing at you. So your CH3 is right here. Oh, I have these too. What do I put on up here?
Chlorine.
I'm going to put my chlorine up here because we're looking at the atom, looking at the bond from the right-hand side. My chlorine would go to the left, just as we did. Remember the cat example that we did? Cat with different socks, different colored socks. That's where the color comes into play. So imagine, let me just draw it. I'm going to draw blue, just to help you to visualize it better. My bromine is going to be red. If I look at the atom this way, my blue would end up on the right or left. Emanuela, you're making a gesture, but can
Yeah, is it left?
It's going to end up on the left. You're absolutely right. So my red will end up on the right-hand side. So now we've rotated the molecule one atom by one atom to make the H go into the board. So now we can renumber everything based on our numbering that we obtained before, and then assign the absolute configuration just as we normally would. So this part is the most difficult part, but it grows on you. And if you want to do more practice problems, I believe there are in the book. I think there will be more practice problems like this in your worksheet. So pay attention to this. And Julia, thank you for raising this question.
Okay, thank you.
Yeah, you're very welcome. So our time's up. Our time is up. So for those of you who don't have any questions, you can feel free to leave. But for those who want to have more discussions, I'll stay behind and we can talk more if you would like.